All right, so let's look at example 1. Consider the sampling distribution of the mean. So the summary statistic is a mean, just like the hamster example. Sampling distribution of the mean of a random sample of size n taken from a population of size big N with a mean of mu and a standard deviation of sigma. So what it's saying is, just use these as like constants. Pretend they've been given to you, right? If big N equals little n, what are the mean and standard error of the sampling distribution? And here, I should show you that there is actually a new little notation that you should know. So the mean of a sampling distribution of means looks like this. So it's a mu, right, because it's an expected value, and expected value are theoretical populations, sort of. But it's an expected value of means. So here, we would put a little x bar. It's a bunch of little means. It's a bunch of little sample means. Right? And same thing with standard error. Ooh, I said standard error. This should also say standard deviation. The special name for the standard deviation of a sampling distribution, because that gets to be really long, and we use that concept over and over again, we just call it standard error. But it's really just the standard deviation of a sampling distribution. Here, it's a sampling distribution of means, so we call it sigma x bar, sub x bar, right? Okay. If our entire population is size big N, and we take a sample, we take sampling distributions of size big N, basically, because big N equals N, then what would be the mean and standard error? Well, the mean of my sampling distribution should be the same, exactly the same as the mean of my population, right? Because basically we're sampling the entire population. Same thing with standard. But think about the standard deviation. Remember, when we're calculating standard deviation, we're getting the average deviations, right? And so when we get the average deviations, that actually ends up, when you take the mean over and over again, that mean is going to be the same every single time, right? So before, if your population had whatever standard deviation, now it's going to be super duper, 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 duper tiny, right? Because you're going to have no standard deviation. You're going to have no spread because you're just going to get that same mean every single time, right? So this is going to be super small, right? Maybe close to nothing, right? Because there's going to be no spread around that mean. Okay. But what if little n, the size of our sample, is very small, and big N was very large? So our population is ginormous. Big population. But our sample is super small. What about in that case? What will our mean of the sampling distribution look like? Well, all we know is that, we don't know for sure that it's going to be the same, right? That's all we can say, really. It might be close, right? Because if you take a whole bunch of these means, right, might be close. But maybe we're going to be less sure. Who knows? But what about if the n is very large, big N is very large, and little n is very small, what would the spread of our sampling distribution look like? Well, in this case, it might be smaller, but it wouldn't necessarily be super small, right? So maybe smaller, but not necessarily super small. All right. What about mu sub x bar? Here we're not sure, right? Is it going to be similar to the mean? Is it to the mean of the population? Is it going to be different? Well, let's think about taking one out. Any one single mean might be very different from the population, right? Any one single mean. But think about taking a whole bunch of those means and then getting the mean of that, right? Whenever you get the mean, you get sort of the middle, right? So here we have this giant population. We take all these samples out. We have all these samples. And then we take the middle of that. That should be the middle of the population, right? So maybe we'll take an educated guess and say that might equal the mu too, right? Not any single one of them. We're not saying that any single one of them is going to be exactly equal to the mu. Some of them will be equal to the mu. But the average of a whole bunch of those means may be equal to the mu because we're always moving to the center. All right. Example 2. Sampling distributions are distributions. What might be the best way to describe sampling distributions? Well, let's think about how to describe regular old distributions. Remember shape, center, and spread? Well, maybe that will apply to sampling distributions. Shape, center, and spread. And we could actually find the shape of it, right? We could find the center of it, for example, mu sub x bar, or if you used something else, like maybe you have a sampling distribution of standard deviations. It might be mu sub sigma, right? Whatever. Also spread, standard deviation, right, of x bar, or you might have standard deviation of little standard deviations, right? And so maybe that's a way we could describe sampling distributions as well. All right, example 3. 3 very small populations are given, A, B, and C, each with a mu of 30, right? So this is a truly small population. There's only two items in this population. There's only 5 items in this one, and there's only 3 items in this one. Match these to the corresponding sampling distribution of the sample mean, n equals 2. Assume replacement. So if you draw 2 out, you put them back. Or else after once, you'll be gone. This will be gone. Assume replacement below. Okay, so let's look at these. This one, it seems to go from 10 all the way to 50. So you could have a mean of 10. You could also have a mean of 50, right? So that's possible here. You could, remember, think about a population where, you have a whole bunch of 10s because every time you draw out 10, you replace it, right? So you could draw out a 10 again, right? So you could get a mean of 10, right? Here you could also get a mean of 10, and here you could also, oh, wait, no, here you can't get a mean of 10. There's no mean of 10 here. Okay, so A cannot possibly go with C, but A could possibly go with A or B, right? I should probably call these 1, 2, and 3, just so that we don't get confused, right? All right. But can A give a mean of 15 or 20, right? Can you put 10 and 50 together in any way and divide by 2 in any way to get 15 or 20 or even 30, 25 or 35? No, right? There's no possible way 10 and 50 can be combined together and divided by 2 in any way to give you 15, right? But here we see that 10, here we can have a mean of 10, we could have a mean of 50, and we could have a mean of 30, which is 10 plus 50, so 60, divided by 2, which is 30, right? And those are the only 3 types of means you could have. So I would say A goes with that one, right? It's very limited. Then I would say B would go with this one, because in B you could have a mean of 10, you could have a mean of 50, but you could have all these means in between. Because if you got 10 and 20 and average them together, that would be 15, right? And so this one has those possibilities, these different possibilities, right? That that this one doesn't have, it's missing, right? But let's move on to this one. So here we know that you cannot have a mean of 10 or a mean of 50, but you can have a mean of 20, 25, 30. And so because of that, we know that this one goes with this one. And also we've used up all the other ones. So here we see that the things you have in your population limits the kinds of means that you'll see in your sampling distribution of the mean. And here it's called sampling distribution of the sample mean, but same idea. All right, example 4. Here are our very small populations again, A, B, and C. Estimate the sampling distribution's means and compare them to the population's mean. Which standard deviation is smaller, the population or the corresponding sampling distribution? All right, so I'm just going to renumber these again. Okay, and let's estimate these means. So here the mean looks like 30. Here the mean looks like 30. And here the mean might be a little bit greater than 30, but still around 30, so maybe like 31 or something, right? And here the means are 30, 30, oops. Maybe I'll put these in different color so that you know I'm talking about the population. So here we know the mean because it's 30, 30, and 30. And what we see is that the sample means, even though our n is small, our n is only 2, right? Equals 2. Even though our little n is small, well, I guess our big N is sort of small too. Here we see that the sampling distribution of the mean, right, the expected value, is very similar to the actual population mean, right? So estimate them, compare them, very similar. Okay. So which standard deviation is smaller, the population standard deviation or the corresponding sampling distribution? Well, it might be helpful if we actually find out what the population standard deviation might look like. So here we have something like, so here's A, B, and C. A is 10 and 50. B is 10, 20, 30, 40, 50. And C is just 20, 30, and 40, right? And so let's find the standard deviations of these populations. Right? The reason why we use standard deviation of the population is because we want it to divide by n rather than n minus 1. So we could just put in all of those. Oh, actually. I wanted to test and make sure I could use these blank ones because then I could just copy and paste across. Okay, so the one that has the greatest spread is A. The one in the middle population here, this one has the middle spread and this one has the least spread. It's sort of closest together. All right. So just to give you an idea, this population standard deviation is 20, right? The spread is 20. But if you estimate this, is this less than the standard deviation of 20? Or greater, right? Well, if you think about a standard deviation of 20, right, that would be this. And another 20 would be that. And usually within 3 standard deviations, you have the entire like almost 99%, right? But here what we see is already at 1 standard deviation, you have almost everybody in there, right? So I would say this standard deviation is smaller. So here, mu sub x bar, that's the same, but sigma sub x bar, I would say, is probably smaller than sigma, right? What about here? So here in, this is now corresponding to B, right? B, A. So here, the sigma will be something like 14, right? And so if I go out about 14, that would be like that, right? 1, 2, oh wait, sorry, that's not 14, that's 5. So 14 would be that. 1, 2, 3, right? And even when I go out to about 1.5 standard deviations, I've basically covered my entire space, right? So here, although the mu sub x bar is similar, our standard error is smaller than our standard deviation of the population. And let's use that same logic for the last one that has a standard deviation of approximately 8, right? And here, let's go out about 8. So 8 would be like that, that, right? And again, we see that although the mu is similar, not exact, but similar, our standard deviation, or our standard error, is less than sigma, right? So one thing we find is that typically the population standard deviation is smaller than the corresponding sample distribution's standard deviation, or what we call standard error. All right, so that is your introduction to sampling distributions.